This is a huge amount of energy. Think, oh, how bad could it be? It can be really bad. It will trip if the current gets to 5,000 amps, all right? Now, here's where the big hazard comes in. So today I'm going to talk about electrical safety when you're doing control work. The deal is that 240 volt electric is, in relative terms, is very safe compared to 480. You say, oh, what's the big deal? It's only twice the voltage. Well, in between 240 and 480, a lot of things happen. At 480 volts, which is 277 volts to ground, you get into things like ionization of dust particles and stuff like that can cause a flashover. And in fact, I had a personal experience with this in the early days of my career when I turned on a panel to troubleshoot it, and it blew up in my face. And at the time, I had a little goatee, and I had a little mustache, and I had, long hair, and I had my hat on, and it pitted my glasses so bad I had to throw them away. It burned off all the hair sticking below the below the hat, took off my eyelashes, took off my eyebrows, took off my mustache, took off my beard, and left me with a nice sunburn. As it turns out, the particular device I was working on, called a combination starter, is exactly the same size and type that Faraz Shalmit used to demonstrate how bad this could be, using a dummy standing in front of one. And they measured the impact against the dummy's chest, and they measured temperatures, and they measured the sound levels and stuff, and they determined that it could damage your hearing, it could stop your heart from the impact on your chest, and of course you could get bad burns. And so this is a real serious thing. I'm old enough to go back in the days when we didn't have a lot of safety gear. Arc flash standards came in maybe, I guess, 20 years ago or so, and all of the electrical contractors now are required to have arc flash gear, and equipment that you work on now, if it's 480 volt, is required to have a plate on it saying what the level of arc flash hazard is. And this is where the issue comes in about the safety factor, because it's kind of unclear how this works. So an arc flash is when the current either goes to ground or goes to phase and generates an arc. And at 240 volts, generally you don't get an arc. You get a short, and it'll flash, it'll bang, it'll burn something off, but you don't get this arc that stays on like a giant welder. So that's why 240 is not nearly as dangerous as arc flash on 480. And 600 volts, of course, and voltage is higher. So the part that's misunderstood is how fuses and circuit breakers work. This is the crux of the whole issue. And what happens is we're dealing with AC power here. So we have a sine wave, okay, and the voltage is reversing and passing through zero at the center, right? So the basic physics law here is that the power is the area under the waves, okay, under the curve. So this area, this is the energy, this is the energy, this is the energy. Okay, so circuit breakers are a mechanical device, and circuit breakers, because they're a mechanical device, they're not really instantaneous. It may take, I don't know, a 20th of a second to trip. Well, in 60 cycles, in order for that breaker to, before that breaker trips, you're going to see 3 full cycles of energy. So the energy released in a fault is all of that energy under the curve there, okay? So we also have what are called peak limiting fuses. And the way that a peak limiting fuse works is that it is able to trip so fast that it will limit the current on the way up the curve. And so now the energy under the curve is just this little tiny piece. So peak limiting fuses came into use as a backup for circuit breakers, and also in cases where you just don't use a circuit breaker, you just fuse it. And the deal here is that the fault current is incredibly high in a lot of places. In your home, your circuit breakers are rated 5,000 amps to 10,000 amps interrupting capacity. What that means is it can open a fault where the current has gone up to 5,000 amps without destroying the circuit breaker, or 10,000 amps. When you get into industry, the interrupting capacities go to 100,000, 250,000 amps. So what happens is that in order for the peak limiting fuse to work, the current must get above the peak limiting fuse's rating. So if I have a peak limiting fuse that will limit the current to 5,000 amps, it will trip if the current gets to 5,000 amps, all right? Now, here's where the big hazard comes in. If I'm working on a panel that's part of the main service, it's pretty much guaranteed that if I get a fault, the current will rise to 5,000 amps because the service can probably generate, say, 20,000 amps without even, breaking a sweat. So you're pretty damn sure that that's going to clear in that little time, and that'll be the energy you have to deal with. All right? Now, the problem is, what happens if the circuit can't supply that much current? And you say, well, why wouldn't it be able to supply that much current? Well, a good reason is that this isn't the main service where I have huge wires coming in and my fuses are right there. This is a sub panel on the other side of the building. The wire runs 100 feet. So now we have to deal with wire resistance. So what happens? Well, you get this short and the arc starts and the wires limit the current. And they limit it to say, oh, just 3,000 amps. But guess what? It's 3,000 amps, all this under here, for as long as it takes to trip that fuse. And because the fuses are intentionally designed to limit the current, but also allow motors to start and stuff with 6 times the normal running current, this is a huge amount of energy. So the reality is, that sub panel you're working on in a building that you think, oh, how bad could it be? Can be really bad due to the fact that you can get way above the peak limit and get many, many cycles. It might be 20 cycles before something trips. That's an enormous amount of energy, just enormous. It's like a bomb going off, okay? So as an example of the machine I was just talking about where I noticed that there was a 480 volt breaker in the top of the panel, that breaker was not to protect against a fault like this. It's protecting, it is, but the fact is that breaker is unlikely to trip quickly due to the fact that this machine is fed by a cable that goes across the building to some panel someplace else. So that makes it really dangerous because of the wire voltage drop and the panel being, if the panel's not the main service, then it may not be able to supply that much current. And this is where the hazard of all arc flash comes in.